go. In this video, we're going to talk about acid and base strength relative to their Ka and Kb values. And when we're talking about acids or bases, we're talking about their properties in water. And water itself, being amphoteric, can either act as an acid or a base. And it itself also autoionizes or breaks apart into hydrogen ions and hydroxide ions. Well, the hydrogen ions get absorbed by another water molecule and form hydronium at a concentration of 10 to the negative 7th molar, which is really small. So the K value, or equilibrium expression for water, would be the dissociation into the hydronium ion and the hydroxide ion. And since water, the reactant, is a pure liquid, we don't include it in the expression. So since for every one hydronium ion, you're going to get one hydroxide ion in pure water, we can say that the concentrations would be equal, and both would be 10 to the negative 7th molar. 10 to the negative 7 times 10 to the negative 7 is 10 to the negative 14. And that's our value for water's Kw, and we're going to find that that's very much related to the Ka and Kb values for acids and bases. Now, when we're talking about an acid, we're talking about something that increases the concentration of the hydronium ion. If we look at a weak acid, what we see is that most of the material will remain in the unionized form, and a very small portion of it will end up in the ionized form. So the acid will give a proton to the water, which then becomes the hydronium ion. This is the conjugate acid for water. And the acid will become its conjugate base. And the reason a weak acid doesn't break apart every time is that this conjugate base is fairly good at holding on to that hydrogen. It has a decent attraction for it, and it doesn't just give it away like nothing. If we look at a strong acid, you can see that virtually all of it is going to be in the product state. So you're going to end up with a very high value for K, because the Ka for an acid is the concentration of hydronium ions times the conjugate base over the unionized form. And you can see that if all of it's in the product form, you're going to have a very high value. Your denominator is going to approach 0, which is going to make the value astronomically high. So for strong acids, we don't even quantify this value. We just say very high. When we're talking about weak acids, however, they only dissociate a small percentage of the time. Say we were looking at an acid that dissociates 5% of the time. That means the relative concentrations would be 5% would be in the hydronium ion, 5% would be in the conjugate base, and 95% would remain unionized. So that would give us a K value of 2.6 times 10 to the negative 3rd, which is relatively low. Because we say if a Ka is less than 1, it's a weak acid. And if it's greater than 1, we would classify it as strong. Now, this is a strong acid is going to result in a lower pH because it has a higher concentration of hydronium ion. And the higher the concentration of hydronium ion, the lower the pH is. If we look at a weak acid, you would not get quite the same. It would have a lesser impact on the pH because you have a lower proportion, at the same concentration, you have a lower proportion of the hydronium ion in solution. Now, when we look at a weak base, it's the same deal. What a base does is it pulls a hydrogen ion off water and results in the formation of hydroxide. Most of the time, that's a generic equation. So a base will react with water to produce the conjugate acid and the hydroxide ion. A weak base will only do this some of the time because it's relatively stable in its form where it hasn't absorbed the hydrogen. However, a strong base, which consists of alkaline earth metal hydroxides, will dissociate into those component ions 100% of the time approximately. So you end up with a high concentration of hydroxide. And that's why the pH of a strong base is going to be higher than the pH of a weak base. So for a base, we say the Kb expression would be the hydroxide ion plus the conjugate times the conjugate acid over the unreacted base form. And the same deal, if you have a low value for Kb, it's going to be a weak base. If you have a high value, it's going to be a strong base. So let's take a look at the acid that we were using in the lab the other day. We were titrating the acetic acid, which is HC2H3O2, and we were titrating it with sodium hydroxide. But this is a weak acid. And the reason we can say that is because when you put it in water, it breaks up, it ionizes and forms the hydronium ion and its conjugate base. But this conjugate base is fairly strong. And the stronger the conjugate base is, the weaker the acid's going to be, because the less likely it's going to be to lose a hydrogen ion. And we can actually quantify it. So if we take the Ka for this process, and then we look at what the conjugate base is Kb values, and we get that from when you have the acetate ion in water, it's going to pull a hydrogen off of water some portion of the time, and it's going to result in the production of hydroxide. These Ka and Kb values will actually multiply by each other. So the Ka is 1.8 times 10 to the negative fifth. The Kb for acetate is going to be 5.6 times 10 to the negative 10th. If you actually multiply those two values together, you're going to get 10 to the negative 14, which is the same as our Kw for water. Now, why can we say that that's going to happen? Well, if we combine these equations, right, and we cancel out species that appear on both sides, which is what you would do, the acetic acid appears on both sides. The conjugate base appears on both sides. And what you end up with as a resulting equation is two waters producing H3O plus and the hydroxide ion. Keep in mind, those two would be considered aqueous, and this is in the liquid state, so we don't include that. What do you have here? Well, you have the same thing that gives you your Kw for water. So it's going to be 10 to the negative 14. So when you combine the reactions, and you combine their Ka and Kb values for a given substance, you're going to get 10 to the negative 14. So the take-home message is, the higher the Kb is for the conjugate base of an acid, the weaker the acid's going to be, because the conjugate base is going to be very good at holding on to those hydrogens, so it will be a stronger conjugate base. That does not imply that it is a strong base, however. There are a select few of these. So when we say a stronger conjugate base, that's relative to the conjugate bases of other acids.